Cloud storage operates under a brutal engineering paradox. Systems like Dropbox and Google Drive have to ingest massive, multi-gigabyte binary files with maximum throughput, while simultaneously orchestrating millions of sub-second latency-sensitive state changes, uploading a gigabyte of video on one side while registering a single keystroke across a dozen connected devices on the other. If you build this system like a standard web application, routing user traffic through a web server connected to a monolithic relational database, it collapses under the dual load. Pushing heavy files directly through an application server creates a catastrophic bottleneck. The servers get tied up moving bytes, starving the database of connection threads and destroying the system's ability to handle small, fast synchronization events. Achieving scale requires abandoning the concept of a remote hard drive entirely. Instead, the architecture relies on three specific design principles. First, the absolute decoupling of the data plane from the control plane. File bytes and file structure must travel completely separate paths. Second, content-defined chunking. Storage must be broken down and deduplicated based on internal byte patterns, not file size. And third, multi-tree state convergence. Real-time synchronization cannot rely on simple event logs to resolve distributed conflicts. Modern cloud storage is a lightweight, distributed metadata registry, orchestrating a separated, immutable object store. In a naive architecture, a client sends a large file directly to a monolithic application server. Routing multi-gigabyte files through the application tier wastes memory and bandwidth. The long upload connection holds resources hostage, starving out latency-sensitive metadata queries trying to get through. The solution is to bifurcate the system. The application backend must never actually touch the file bytes. In this decoupled flow, the client starts by sending a lightweight token request to the metadata server, asking for permission to upload a specific payload. The metadata server authorizes the request, replying by issuing a pre-signed S3 URL back to the client. This URL acts as a temporary cryptographic passport. The client then takes that pre-signed URL and uploads the heavy file directly into object storage. The massive data payload bypasses the metadata server entirely. By offloading the binary transfer, the upload speed is now limited strictly by the user's local ISP bandwidth and the immense throughput capacity of the object storage provider. Separating the heavy lifting of moving bytes from the complex logic of managing folder structures is the only way to scale ingestion. To handle massive uploads efficiently, files cannot be stored as single monolithic objects. They must be chunked into smaller pieces to allow for parallel uploads and easy resumption if a network connection drops. A simple approach splits a 10 megabyte file into fixed 4 megabyte chunks based on arbitrary byte offsets. But fixed chunking introduces the boundary shift problem. Watch what happens when a user types a single new letter, inserting 1 byte, at the very beginning of the file. That single byte shifts every subsequent boundary downstream, changing the local content inside every single chunk. When the contents change, the cryptographic SHA-256 hash for every chunk also changes. The system no longer recognizes the data, breaking deduplication and forcing the client to re-upload the entire 10 megabyte file just to sync one new character. To fix this, systems use content-defined chunking, which utilizes a rolling hash algorithm scanning over the data stream. Instead of cutting the file at fixed intervals, CDC dynamically places a chunk boundary only when the rolling hash output matches a specific bit pattern condition in the data itself. If we simulate that 1 byte insertion again, only the very first boundary adjusts. Because the chunk divisions are anchored to the actual content patterns, all downstream markers remain perfectly intact. CDC preserves the cryptographic fingerprints for the rest of the file. Before transferring bytes, the client queries the database with these hashes and simply skips uploading any chunks that the system already holds. Chunk boundaries must be determined by local byte content, not file offsets. This mathematical alignment makes deduplication and delta syncs possible at scale. While the data plane handles ingestion, a separate sync engine must coordinate that state across millions of devices in real time. A basic event-driven model, where clients just push local file system changes to the cloud sequentially, breaks down immediately. If two users edit the same file offline and reconnect simultaneously, sequential event logs lack the context to resolve the conflict. To maintain consistency, engineers built the nucleus engine, abandoning event logs in favor of treating sync as a mathematical reconciliation of three distinct state trees. This diagram illustrates the three-tree architecture required for state convergence. The remote tree represents the authoritative cloud state. The local tree is the file layout on the user's disk. The synced tree represents the last fully synchronized state between the two. The synced tree acts like a Git merge base. By referencing this baseline, the sync engine can deterministically calculate the precise direction of any file modification. For example, if a file in the local tree differs from the synced tree, but the remote tree still matches, the system knows this is a local edit, triggering an upload. Conversely, if the remote tree differs from the synced tree, but the local tree matches, the system identifies a remote change and triggers a download to the local device. Without a centralized merge base, systems cannot distinguish between an intentional offline deletion and a missing remote update. The three-tree model prevents that ambiguity. We can see these principles work together by tracing a single edit through the entire lifecycle. A user types one new word in a synced document on their laptop. The client app's content-defined chunking algorithm recalculates the rolling hash over the file. It isolates that one byte change to a single new delta chunk, leaving the hashes for the rest of the file untouched. The client queries the metadata database with the hashes. Recognizing a deduplication hit for the unmodified chunks, the server replies with a pre-signed URL to upload only the single new delta chunk. With the chunk securely in S3, the architecture shifts to synchronization. The metadata database links the hash to the file version, firing an event into a message queue. A notification server consumes this event, pushing an instant WebSocket ping to the user's secondary laptop. Receiving the ping, the secondary laptop evaluates its three-tree state. It realizes it needs the new delta chunk, fetches it directly from object storage, and stitches the file back together locally. This architecture isolates heavy binary payloads, amortizes storage via content addressability, and rigorously maintains distributed state at planetary scale. The structure of the system is just as important as the storage.